Good morning, everybody. My name is Petr Kluson, and I am currently Scientific Vice President of the European Federation of Chemical Engineering. I'm very glad to be here this morning. I'm very glad to be here with Professor Enrico Drioli, with Martin Pu. Martin is the head of the Secretariat, Scientific Secretariat of EFCE, and with our plenary or spotlight plenary speakers. Just very briefly, spotlight talks were actually developed or designed 2 years ago during the pandemic situation as a tool how to approach our community, how to disseminate the results under difficult circumstances for popularization of our achievements. And of course, it continued last year, the previous year, and this year we have the third in the series. We strongly believe that, of course, pandemic situation brought us many difficult moments. However, some designed formats, tools, means were found as very effective and useful. So that's why we are here today as well. For this series, we have 8 spotlight talks, and we plan to organize another round in the autumn. It is a very effective way how to communicate, how to share our results, and how to be together. In spite of, we strongly believe it will be able to meet face to face. We wish to retain this format for the next year as well, and to continue with it. So I'd like to express my thanks to Professor Drioli for being active, for preparing it, for reacting in a very positive way when we approached him for organizing this morning meeting. I'm expressing my very deep thanks to Martin, who organized basically everything regarding invitations, regarding the technical part. So thanks a lot. Many thanks once more to plenary speakers, and now I'm passing the virtual stage to Enrico. So it's your turn, Enrico, now for introducing the speakers. Thank you.
Thank you very much, Petr. Very pleased to be here. We have to thank the European Federation to promote this kind of activity, and Martin and Petr for all the collaboration in the organizing all details. You know, membrane engineering is one, in our personal opinion, and in the opinion of the people really working in the field, is one of the technological areas able to contribute significantly to the realization of what is called today a process intensification strategy. I'm personally assuming that the solution of some of the major problem we have today, from water stress to energy problem and many others, is related to a strong integration of progress in material science for sure, but mainly in the process engineering side. The real success in solving problems cannot be just related to the new materials, as some people assume, that has to be related to the new processing. This is a personal opinion. In some country, is not accepted. If you want to go in some country, if you are not a material scientist, you will never become a professor at university, some people are telling. But my position is very different, and I like to express this position, supporting the fact that we need today more and more attention to developing advanced process engineering, and process intensification is the way to formalize this concept. Now, membrane engineering is a term that years ago was not existing and has been growing significantly in the past century. Now, everything started in the 70s, in the 80s. You know, this working party has been suggested by Professor Behrens already early 80s. But if you look the statistic or bibliometric studies, you will see that has been growing significantly in the past centuries, but always linearly. If you go from the 70s to the 2000s, there is a constant significant growing in the impact factor, in the number of citation, in the money invested in the field, but was a linear growth with big success, by the way. Membranes was not existing in real life. Today, to give you an example, membranes is a dominant technology in desalination and in wastewater treatment. If you go all around the world where people need to have solution to the water stress, and in the Middle East, to give you an example, and many other parts of the world, traditional thermal system, basically there is no single penny that will be invested in traditional thermal technology for solving the problem. MSF, MFD, etc. basically exist only in terms of maintenance. Everything in all the Middle East, for example, in the next couple of decades at least, is related to the investment in membrane technology, 100%. And the data, not from membrane people, but the data from all the international organizations are just confirming this kind of situation. Totally unexpected 30 years ago, 30, 40 years ago. That situation was not the same at all. What is interesting, however, what is more interesting from my point of view, at the same kind of phenomena is going to take place in some other areas. First of all, if you make the same statistic on the growth of the attention, the level of visibility and the impact of membrane engineering in research and in real life, I was mentioning that in the past, the millennium was growing linearly. Check from the 2000 on. You will see that during these first 22 years of this millennium is growing now exponentially, no more linearly. There is an exponential growth of the interest in different fields, starting from the traditional pressure drive and membrane operation, but what is more interesting, in new field that in part unknown to the large public, from membrane distillation, thermal system, but based on membranes, or membrane crystallizer, membrane condenser, membrane, any kind of membrane contactor system already existing in traditional unit operation is now going to be reconverted based on membrane. So we have membrane crystallization, membrane distillation, membrane condenser, membrane emulsifier, etc., etc. It's not the only one that will contribute to the solution of the problem existing, but for sure, in the last 22 years, what was before a linear increasing in the attention, in the investment, etc., is now going to be an exponential attention. And there are countries, starting from China to give an example, where the success, China has been always an importer of processing on big plants from all around the world. If you read the American Chemical Society reports, you will realize that people in the United States are starting to be worried, and they have to be worried, because China in the last 5 years is becoming now the #1 exporter of process engineering, of big plants. And this is published not by membrane people, but by the American Chemical Society. And now if you are an expert and you read carefully the report from the American Chemical Society, you will realize that all the case studies that they've been analyzing are the one in which a membrane unit has been introduced in the overall big system, syngas production, methanol production, water purification, etc. But in all the system in which China today is an exporter of advanced technology and is no more buying plants, is a system in which at least 1 or 2 unit operations are based on membrane engineering. Very interesting, very consistent with the big result that I was mentioning before, the significant growth in the attention, in the impact of membrane engineering in any sector. That's why I think it makes sense to have this kind of meetings and to continue the activities of all the organization interested in membrane. So I like to start our work from now, and I hope that this meeting will be useful, and if there will be from the participants any feedback and any requests for more information, detail, contact us, contact myself, Martin or Pet or Alessandra Criscuoli, that will serve as much as possible as help to me in handling the session. And we will be very pleased to give more information if necessary. Alessandra Criscuoli, that I like to introduce now, she's a senior researcher at the ITM. ITM is an institute of the Italian National Research Council, equivalent to CNRS in France. And she's a chemical engineer. And by the way, membranes is a very multidisciplinary field. The people talking today are mainly chemical engineers, but we also have chemists. Elena Tocci, she's a chemist, or people expert in physics, in medical application, etc. Alessandra will speak to you on the Exergy analysis and new metrics to assess the role of membrane operation for sustainable development. Please, Alessandra.
Thank you very much for the kind introduction. I'd like to share the screen. And can you see? Yes?
Yes, we can see it. Yeah, thank you.
Okay, so good morning to everybody. And as Professor Drioli said, today I will talk about the Exergy analysis and new metrics to be used to evaluate the sustainability of membrane operations. And in particular, I will start with a brief, only one moment. Okay, on a brief introduction on sustainable development and process intensification theory. Then I will talk about the Exergy analysis, giving some basic definition and some case studies as examples of application. And then I will also introduce some new metrics defining the logic of the process intensification strategy. Again, I will start with basic definition and some example of application. And finally, I will move to concluding remarks. So one of the first definition of sustainable development is that of the World Commission on Environment and Development, already in 1987, so many years ago. And it states that sustainable development is a process of change in which the exploitation of resources, the direction of investments, the orientation of technical development, and institutional change are all in harmony and enhance both current and future potential to meet human needs and aspirations. Of course, these principles are valid today already, and normally sustainable development and sustainability happens at intersection of three main domains, and the economy, environment, and society. And to establish if a process of production or a process of separation or whatever process is sustainable or not, some indicators have been proposed. Economic indicators, which refers to investments, profits, values, and taxes. Environmental indicators, which refer to resource usage, energy, material, land, and also emission effluents and waste related to certain production. And then social indicators like employment situation, health and safety at work, benefits, troubles for the community. So when these three domains are just reached all together, then we can talk about sustainable development. And strictly linked to the process in sustainable development is the process intensification strategy, which has been introduced in late 2000, so already 20 years from now. And it consists in the development of processes which are characterized by a substantial decrease of the equipment size production capacity ratio, a substantial decrease of the energy consumption, as well as a decrease of waste production. So thus resulting in sustainable technologies. So the process intensification theory is in fact related to the same principle of the sustainable development. So they are strictly linked together. And the membrane technologies respond efficiently to the requirement of process intensification strategy. In fact, membrane technologies are characterized by several properties. For example, as listed here, they have a high capacity size ratio. That means reduced land requirements for the plant. No need of chemicals, then that means reduced pollution. low energy consumption, that means reduced use of energy, no moving parts, that means easy in operating, modularity, easy in scale up. So there are all these membrane features that naturally make membrane operations quite attractive to reach the goals of the process densification strategy and sustainable development. And in last years, a new class of membrane operations, like Professor Drioli said in introduction, the membrane conductors family, let's say, has appeared, and together with membrane conductors, new unit operation can be covered, like gas, liquid extraction with membranes, of course. And with respect to traditional packet towers of bubble column, which are normally used to carry out this kind of separations, with membrane conductors it's possible to have some other properties quite interesting in terms of sustainable development. For example, we have no dispersion between phases. That means we do not need further separation downstream, so we are a reduced impact on the production line. We do not have loading or flooding limitations that normally are present in a bubble column or packet towers. Then we have the possibility to operate in a wide range of flow rates. We do not have foaming, and then we have an efficient mass transfer, and also we have a constant interfacial area. That means that we have an uniform performance along the entire unit, which cannot be really obtained in traditional tower or column because we don't know exactly in this case where the two phases will be in contact. In vice versa, with membrane conductors, we also have this possibility. So among the different goals of sustainable development, for sure, the reduction of the energy use is quite important, especially today. We need to optimize in an efficient way the use of the limited energy resources available. And in this respect, the Exergy analysis are quite interesting for the process optimization and by the minimization of the Exergy destruction linked to a specific process. But first of all, what is it, Exergy? Exergy can be defined as the part of energy that by reversible transformation can be completely converted from one form to another form. So it's the maximum amount of work that we can obtain from a certain system because of its evolution from its state to the environment with it is not in equilibrium. So the non-equilibrium conditions with respect to reference condition makes possible to have work from our system. And in fact, for any real process, it is not really like that, but we always have some entropy production during this evolution. So we always have some exergy loss by irreversibility. Then the exergy analysis are used to evaluate the dissipation of process. So they are useful to identify the weak points of the process and try to act on it. In particular, the exergy analysis can help in identifying the part of the plant less efficient, but also to state the convenience of a non-operative process with respect to traditional one. In fact, we can calculate the entropic losses, entropy production, for the two processes and then compare the two in order to have an idea how much it is efficient, one process with respect to the other. So we take into account this aspect in our energy evaluation. And in how to calculate the exergy? Well, we can use an exergy balance. This is just the basic one reported here. We have this equation where we have the entropy production, which is irreversible, is given thanks to the electrical exergy supplied to the cycle, the thermal exergy supplied to the cycle, and then the exergy variation between the outlet and inlet streams involved into our system. So for any system, we are able to calculate through this kind of balance, to this kind of equation, our production of entropy. So to evaluate the irreversibility of the process. And concerning the different streams, normally we are able to calculate the exergy of each stream considering its temperature, pressure, and composition. So it states with respect to what is the reference condition. That means the temperature, pressure, and composition that we have chosen as reference state. And well, with this kind of approach, we are able then to calculate the reversibility of process and try to optimize the exergy efficiency of the process, then try to use as much as possible in the best way the energy involved in a process. And as a case study, I would like to share with you some kind of application of exergy analysis to desalination. Desalination is today a crucial source of fresh water, and it is expected in next future desalination plants will considerably increase due to the water scarcity issue and also the problems of water stress experienced worldwide. And in particular, as Professor Drioli said, reverse osmosis are now dominant technology in desalination processes, but anyway, any desalination process requires significant quantities of energy to achieve the separation of salts from seawater. So we can try to apply exergy analysis to see how they works and how they can be optimized. And in particular, here it's reported, for example, a simple scheme of a reverse osmosis unit. What we have the seawater, which is pumped through a high pressure pump towards the reverse osmosis module. And then we have the permeate production, which is the fresh water without salt, and the other stream, which is the retentate, consisting in a highly concentrated stream we call brine, highly concentrated in salts, which have been rejected by the reverse osmosis unit. Normally, when we have to analyze any flow sheet, what we consider is, of course, the productivity of the system. That means the fresh water flow rate, in this case, that can be obtained, and also the quality, the selectivity of the system, then the composition of the fresh water as well. And so these are normal parameters that we consider when we analyze any flow sheet, any system for separation or production. However, when we would like to apply to this flow sheet also exergy analysis, then the equation that I showed you before must be applied as well. And then we can calculate, considering the terms that I showed you before, the electrical entropy, the thermal, electrical exergy, the thermal exergy, the difference of exergy of streams involved, and then finally we can obtain the production of entropy linked to the process. And as you can see here, even if reverse osmosis units are quite well used in desalination, there is still room for trying to minimize the exergy loss due to the desalination itself. So how to do that? So this is the balance for all the system, telling us that, of course, we need to optimize somehow and to reduce this entropy production. How to do that? Well, we can do that by considering and applying the exergy balance, not to all the system, but for each component of the system included in the system. So the high pressure pump, the reverse osmosis module in this case, and the valve that is used for liquid pressure reduction. And as we can see here from this kind of analysis, it resulted that the highest exergy destruction is in the membrane module for the permeate and brine production. That means that we have to somehow consider this kind of loss, because we cannot do too much on the membrane module, so we cannot act too much on it. But what we can also do is to act on the throttling valves for liquid pressure reduction, which is another major source of irreversibility for our system. And if we do that, in fact, by, for example, using some energy recovery devices, what we can notice that we can have a substantial improving exergetic efficiency of our system, moving from 28% without any kind of an energy recovery device up to more or less 49%. So this is just an idea on how I can act on my system in order to minimize the entropy production and then try to optimize it in terms of overall energy use and consumption. As I said before, reverse osmosis is quite used in desalination, but it produces not only the fresh water, but also highly concentrated brines. And that means that these brines must be disposed somehow. Usually, these brines are rejected back to the oceans, to the sea, and also into deep well. Today, we know that it's not possible to go on in such direction, but we should do something different because of the environmental impact of these brines. And then a possibility is to couple other membrane operations working on the reverse osmosis brine. In particular, the membrane distillation and membrane crystallization brines, operations which are not limited by by osmotic problems like reverse osmosis can work properly on the highly concentrated brine, allow the possibility, allowing us to obtain a higher water recovery factor and then a high reduction of the volume of brine cells. So working well in the logic of the process intensification strategy. So with this scenario in our hand, we could try to consider another type of flow sheet as reported here, where the reverse osmosis brine is just not discharged, but is just sent to a membrane distillation unit. And also for this, then we have an integrated membrane system with RO, MD working together. And in this case, of course, we can still evaluate the performance of these systems considering the normal, let's say, indicators. So the brine flow rate, concentration, freshwater flow rate, and freshwater concentration. And in this case, we can notice that if we compare the reverse osmosis unit alone with respect to the integrated reverse osmosis membrane distillation system, we have a substantial reduction of the brine flow rate and also much more highly concentrated now, and also a substantial increase of the freshwater flow rate, which is also more pure, less concentrated. So in this sense, it seems that the integration of membrane distillation with the reverse osmosis unit is quite interesting because it improves the performance of the systems in terms of productivity, reduction of the volume of brine to be disposed, and also quality of fresh water. But how it impacts in terms of exergy. So how the introduction of membrane distillation unit impacts on the production of entropy and then to the destruction of some available work from the system, available energy. And well, we can, of course, calculate this by using the equations that I showed you before, and in particular in this table are just compared the Exergy results for the two flow sheet, the reverse osmosis alone and the reverse osmosis coupled with the membrane distillation unit. And you can see here that there is in fact a big difference in entropy production, almost double for the integrated reverse osmosis MD unit, and this is mainly due to the high thermal consumption of the membrane distillation unit. In fact, the membrane distillation needs some thermal heat in order to make the evaporation of the brine, and then we are supplying to the cycle some electrical thermal input and then thermal exergy. But then the thermal point seems to be the weak point for our system. So how to try to optimize in this sense all the membrane distillation unit in order to make it also attractive in terms of exergy and point of view? Well, the first thing that we can think about is to use some renewable energy, for example, solar energy, also some waste heat if available. In fact, if we just consider our brine entering the MD unit at the desired operating temperature, we do not need to supply heat anymore. And then you can see here the two Exergy let's say, efficiency, the entropy production for the two systems are quite similar, but in the same time, we are gaining in terms of fresh water production and volume of brine to be disposed. So we have a more efficient system at parity of Exergy performance. But in another point to act on is to try to improve the Exergy efficiency of the MD module. Here we can do something. In case of the reverse osmosis module, they are quite well established. They are just well commercialized, but MD is still under development stage. So we have still some place for working on trying to improve the Exergy efficiency of MT module. For example, reducing heat losses in the MT unit. This can be done by considering new membranes. And in fact, there is a lot of research, for example, on localized heating of the membrane surface to try to use as much as possible. It's a more efficient way the heat inside the module. And also we can work on the module itself, for example, by reducing the heat transfer resistance in the module. And another point interesting is also to try to develop modules with internal heat recovery. All these points are possible points of action to further improve the membrane distillation unit and then to further improve its exergetic efficiency, also energetic, but also exergetic efficiency. And of course, the MD unit is giving us a highly concentrated brine. So another approach to be considered is, for example, to couple the MD brine to a reverse osmosis, reverse electrodialysis unit. So we can try also to analyze this kind of flow sheet. Reverse osmosis unit sending its brine to membrane distillation unit, which is sending its brine to a reverse electrodialysis unit. So we will have electrical energy to supply to reverse osmosis, thermal energy to supply to the MD unit, but we also have a gain in electrical energy produced in the RED. And in this way, we can produce much more water, but also electrical energy. So this is another approach trying to optimize the performance of the systems. In fact, if we look at the entropy production of this integrated system, we can notice that without any energy recovery device of the high pressure brine, reverse osmosis brine, and without the reverse electrodialysis unit, we have a quite high entropy production. But if we introduce the pressure recovery device, we have a gain in the entropy production because it is reduced, but then we can also have a substantial decrease in the entropy production when we couple the reverse electrodialysis unit to the system. So the optimization of the system allows us to substantially reduce the entropy production, then substantially improve the Exergy efficiency of the system. Of course, another possibility, and this is just without any recourse to external thermal energy supply and so on. So just considering the thermal energy needed for the MD unit. And another possibility is also to use that the membrane crystallization rather than membrane distillation on the reverse osmosis brine. In this case, we still have the thermal energy needs of the plant because membrane crystallization is working like MD, so it needs thermal energy to be supplied to the cycle. But what we have here is the production not only of fresh water, but also of valuable salts. And it has been calculated that the gain of the sale of salts was able to cover desalination costs, even if no thermal energy was available. So also research in this direction could be interesting in order to improve the Exergy of the process in desalination field. And now I would like just to pass to the other part of the presentation, just briefly, and that means the new metrics, which are another type of tool to try to calculate how the membrane operation can work in terms of process intensification strategy. And in particular, these metrics have been defined to compare membranes to traditional process in terms of productivity size ratio, productivity weight ratio, and also flexibility. In this respect, we define two different types of flexibility. Flexibility, first definition, as the ability to handle the variations that may occur during the life of the plant. That means a variation in the temperature, operating condition like feed flow rate, concentration, and so on. And the other definition of flexibility is the ability to be applied in different cycles of production. So that means if my module, my system is able to be applied in different cycles of production without changing, without redesigning everything, removing units and then replacing them, but just changing the final type of operation for the same module. And finally, another index that has been defined is the modularity, which aimed at the comparison of the variation of size of the membrane units with respect to the traditional one when there is a variation in the productivity plant. And in the case of membrane unit, we will refer to the variation in the membrane area, while in the case of traditional unit, we will refer to a variation of the size of the volume. Well, these metrics are strictly linked to the sustainability domains, as it is reported in this table. For example, the productivity size ratio is linked to the economic environmental domain because smaller size are beneficial for land saving. Productivity weight ratio linked to economic domain because lower weights reduce transport and installation cost. Flexibility links again to the economic domain because high flexibility allows to handle variation in operating condition as well as different processes in the same plant. And finally, modularity is still linked to economic domain because high modularity helps in plant scale up and scale down. So briefly, because I see the time is running, as an example of application of these new metrics, I would like to share with you some data on the sparkling water production that we analyzed some years ago. Here, in the traditional system used for the sparkling water production is reported where a packing tower is used to partially deoxygenate the water to be carbonated, and then the final CO2 content is reached by injection of CO2 directly into the deoxygenated water. So two steps are needed for obtaining the final results. Vice versa, on the right side of the graph, it is reported a membrane contactor unit where hollow fiber are considered, and the hollow fiber allows the simultaneous transfer of CO2 from the gaseous phase into the water and the oxygen from the water into the gaseous phase. So both processes are carried out in the same unit, and directly from one unit, we obtain our final target, the oxygenated sparkling water. We compare these two systems for same feed stream at parity of performance, same exit stream. And here I just summarized the results that we obtained in productivity size ratio is quite higher than 1, and then is in favor of the membrane module, like also the productivity weight ratio. So the system with membrane module is well performing in terms of productivity size and productivity weight. And also concerning flexibility, we reached results of much higher than 1, and particular for flexibility 1, so the capability of handling different variation in operating conditions. In the case of the packing tower, there was a fail in treating higher feed flow rate because of flooding limitation. And concerning the flexibility too, so the ability of using in different operations, the same module to be used in different operations, we also have a good results higher than 1. So in favor with membranes, for membranes, because the traditional system, the packet tower, can be applied also for liquid-liquid operation, while for membrane system, membrane contactor can also cover liquid-liquid operation, liquid vacuum operation, and membrane osmotic distillation. So we're able to use the same module for different operations. And finally, also the comparison in terms of modularity was in favor of the membrane system. So membrane system behave quite well in terms of process intensification strategy with respect to traditional units. Just briefly here, new metrics can be also used not only to compare traditional units with membrane operation, but also different membrane units. And for example, here I reported the results in terms of productivity size ratio for 3 different modules used for the same process. Direct contact membrane distillation step. So the different module, of course, present different features, and then this productivity size ratio could help us in the choice of the best module for our process. In particular, in this case, the module M3, which is hollow fiber, has to be preferred in terms of productivity size ratio at parity, of course, of separation efficiency. And so, moving to concluding remarks, as I said before, sustainable development is becoming an urgent need to preserve our planets for future generations. And in this context, membrane operations can play an important role. And Exergy analysis, also new methods, can help us in identifying the different plants of the part of the plants less efficient, and also in analyzing our membranes in terms of performance for process intensification and then sustainable developments. And before leaving you, I would like just to share with you this notice. Because in occasion of the celebration of the 40th European Membrane Society anniversary, the Institute of Membrane Technology and the University of Bologna in Italy are organizing a special edition of the Euromembrane to 2022 in Naples, in Sorrento, Naples, at the end of November. The registration is now open, so you're all welcome to apply and to contribute. And with this, I would like to thank you very much for your kind attention.
Thank you very much, Alessandra. We have a couple of questions. Late with time. So, can you read the first question?
Yeah, I have maybe to go out from, okay, one moment, I have to.
I can read for you if you like, by Cipollina.
Yeah.
Have you considered to introduce some metrics accounting for the value of flexible operation in some membrane processes, which allow for a direct coupling with renewable energy? No batteries? That is the question from Andrea Cipollina, University of Palermo.
Because I cannot see the chat. So if I had considered to have the metrics.
Some metrics accounting for the value of flexible operation in membrane processes, which allow a direct coupling with renewable energy.
Yeah. Direct coupling. Okay, it could. Yeah, sure. It should be a nice step to follow. Actually, yeah, the metrics I consider were just those I showed you before. But in perspective, the combination, of membranes with renewable energy and new metrics to identify, to try to characterize this kind of new system in terms of efficiency and intensification strategy will be, of course, of interest. Will be a next step, but actually we did not define for that system.
But I can add that it is one of the approach that is in progress. There are situations with both solar energy, particularly solar energy, or the waste heat has been considered, and just that, the direct coupling. Anyway, there is another question that which is the second one? I don't see the second one.
No, I see. Now I exit from the screen. I see only one of Andrea Cipollina. Yes.
Martin, is the second question? No.
No more question.
No more question. Okay.
Okay.
One more appeared now. Yeah, there is one more, which is the impact of the quality of the inlet water for RO important, negligible.
Sorry, the impact, I don't know why I cannot see the question, but yeah, can you repeat, sorry?
Yeah, which is the, from Helen Rude-Barman, which is the impact of the quality of the inlet water for RO? Is it important or is it negligible?
Very important.
Oh yeah, sure. The quality of RO, yes, it is quite. The seawater from RO is quite important. In fact, now I just make the examples today, starting from the seawater directly fed to the reverse osmosis units. But in reality, we also had to consider some pretreatment steps like MF and F and whatever before reaching the RO, and then also Exergy analysis on this kind of train, let's say, of membrane operations have been carried out. But today, just for question of time, just to try to focalize more also on membrane distillation as a new operation, new membrane operations for improving the freshwater production and reducing the brine disposal. I just focus on that side, but for sure,
it's very
treatment is quite important as well and must be considered. Yes,
I can give a number. In real plant, here running plant, huge plant we have today for desalination, 60% of the operating cost is just in the pretreatment due to RO units. So the question is, the answer is yes, must be very significant the pretreatment to have the quality of water appropriate for the membrane we are using. And about 60% of the operating cost roughly is just in the pretreatment, not in the RO units. I think there is no other questions. I don't see any other questions. Thank you very much again, Alessandra.
Thank you, everybody.
We can move to totally different topics. And the second presentation will be given from Adele Brunetti. She's a senior researcher at the ITM, at the Institute of Membrane Technology of the CNR. And she's a chemical engineer, and she's mainly working on the membrane reactors and CO2 purification, extraction, hydrogen, etc. The title of the presentation will be CO2 valorization through innovative membrane system as a promising environmental pathway to biofuels. Please, Adele.
Yeah, thank you very much for the introduction.
No mask, Adele.
Oh, yes, I'm removing it at the moment. Yes. Okay, so I don't know if you can see my screen.
Yep.
Okay, so the presentation of today will be focused on the last achievements that we obtained on the use of membrane technology for the valorization of CO2, in particular with the aim of proposing membrane technology as a way to promote sustainability in the production of biofuel. So the outline of my talk, I will spend a few words about the carbon capture, utilization, and storage. So some words about the introduction on a membrane reactor, and I will present two case studies related to the conversion of CO2 in membrane reactor. The first case study will be dedicated to the analysis of the heterogeneous catalysis, in particular describing the results that we have obtained in the production of the methyl ether from methanol dehydration. And the other case study is on the photocatalysis in membrane reactor for producing biofuel. And then some final remarks. So when we speak about greenhouse gas emission, we know that most of greenhouse gas emission are referring to CO2. And we know that around 70% of the CO2 that is today produced is coming from the use of fossil fuels. So both from stationary and transport application. Up to a few years ago, the keyword was CCS, carbon capture and storage. Today, we speak about CCUS, that is carbon capture, usage, and utilization and storage. So this is in the final aim, not only to reduce emission, but also to convert the CO2, pursuing negative emission. So in the meanwhile, as alternative solution to fuels, to the use of fossil fuel, we have also heard about the famous Green Deal, and in particular to the use of hydrogen as a new vector of energy. And we know that there are a lot of money that are now going to be spent by European Union in the logic of promoting the use of hydrogen for climate action. So how do we think that we can fit these two necessity. So from one side, the carbon capture and utilization, and on the other side, the use of hydrogen. A big problem for the hydrogen is not only the production, because we can produce green hydrogen with electrolyzers, for example, but another issue is about the transportation and the storage of hydrogen, because in the case of transportation, we should use dedicated pipelines, so we should spend a lot of money in constructing new pipelines, or we should use current pipelines that are used for natural gas or methane, but in this case, the hydrogen should be diluted with methane at a percentage lower than 3% in weight. So an alternative to this for the storage and the transportation is the production of biofuel. So that in this way, we have a liquid hydrogen carrier that can be easily transported, and that in the meanwhile represent also a way to store the hydrogen. So the idea is to convert carbon dioxide and hydrogen to produce biofuel, and in particular methanol, because methanol is one of the so-called platform molecule for producing a lot of other chemical components that can be fuels like the methyl or can be also intermediate like olefins. Here in ITM, we are coordinating a project is funded by Brunetti. This project is called BioValue, and in this project, the scope was to redesign the process, introducing membrane operation. So in this case, we used the membrane condenser for removing water vapor from the biogas stream, and then gas separation for separating biomethane from the treated biogas. But at the end, we said, okay, now we have a CO2 rich stream. What can we do with the CO2 rich stream? So a big issue is also how can we propose membrane technology also for treating this CO2 rich stream. The idea was to use membrane reactors. Membrane reactors are a well-known technology that represent the most significant class of the so-called multifunctional reactors, because it's possible to carry out reaction and separation in the same vessel. And in the past, they were proposed as one of the technology that well fits the logic of process intensification, because they pursue the footprint reduction, they pursue the modularity, all the metrics that Alessandra explained just in the previous presentation. And membrane reactors were successfully scaled up until TRL7 and TRL8 for what concerns the hydrogen production. But the membrane in the reactor cannot only have a separating function, so not only for removing one product from the reaction volume, but can have also other function. Can have the function of distributor, so to distribute in a controlled way one of the reactant in the catalytic bath, so to control the progress of the reaction, control the hotspot, control the production of secondary products, but can be used also as a contactor. In this case, the membrane can have a catalytic function. It means that the catalyst can be deposited in the membrane, embedded inside the membrane matrix, or the membrane can be inherently catalytic. And in this case, the membrane works like a mirror. It means that exposes the catalyst to the reactants, and it has various advantages, like a better exposition of catalyst and reaction, a better recovery of the catalyst once the catalyst is expired, and a higher stability with respect to packet bed. So the first case study is dedicated to the conversion of CO2 of gas from biomethane plant using hydrogen coming out from renewables. So how can we integrate membrane reactor in the scheme that I showed you before? We can work in two different ways. The first is to integrate a double stage membrane system where a first membrane reactor allow to convert CO2 and hydrogen in methanol and water, and the second step where the methanol produced can be converted then in the methyl ether. The ideal situation would be to have only one multifunctional membrane reactor where the separation, where the conversion of CO2 and hydrogen to methanol and then the methanol to the methyl ether is occurs only in one system. But we are not at this stage at the moment. We are working on it, and I hope in the future to present results on this aspect. Today, I will focus on this stage. So on the use of a catalytic zeolite membrane reactor used as a conductor for the methyl ether production by methanol dehydration. So just a few words about the methyl ether. The methyl ether is a product that can have various uses, can be used as a propellant, as also fuel, also as additional fuel, for example, to diesel. And it can be considered a biofuel because if we look at this figure, we are producing this from CO2 coming from renewable and hydrogen coming, for example, from electrolyzers. So the reaction that we have is a dehydration reaction where the methyl ether is produced by methanol, and we have as other product the water. This is usually carried out in traditional reactors using catalyst, acid catalyst, so gamma alumina and zeolite catalyst. But the main issue of this reaction is related to the catalyst deactivation induced by water vapor that absorbs on the catalytic sides and reduces the performance of the reactor. So the idea was, okay, can we develop new strategies to enhance the conversion of the reaction, but also to enhance the stability of the performance of this unit in the logic of using this unit in a real operation plant. So the idea was to use a zeolite membrane. In particular, we used a ZSM5 zeolite membrane, where the passage of a continuous flow through the catalytic membrane can promote the removal of water from catalytic sites, reducing thus the catalyst deactivation and thus improving the stability of the reactor performance. We used in particular two membranes provided by IKTS in Germany. These membranes were similar for what concerned the zeolite layer, but they had a different support. In one case, we had alumina support. In the other case, we had titanium support. So I will not go too much in the details of the results, but I want to show you just the main numbers that we obtained. Here you can see the conversion as a function of temperature. And you can see that, of course, in this case, since the reactor does not work with a membrane operating as a separator, but only as a conductor, we cannot exceed, in this case, the equilibrium of traditional reactor equilibrium conversion. However, as you can see here, we obtained very good results, very close to the equilibrium that, of course, have a functionality with the space velocity that we use. But an important result was that, in this case, the methyl ether reaction selectivity was 100% at all investigated condition. It means that we did not have secondary products like usually occurs in traditional reactors where the methyl ether selectivity was close to 92–95% with the production of other secondary products. And this is one of the main results that we obtained in the case of the that confirmed that the advantages in the use of membrane reactor. The same trend with different results were obtained using the membrane with titanium. Also, in this case, we had a significant advantage related to temperature and space velocity. But an important aspect that I want to focus is that when we speak about membrane engineering, as Professor Drioli said, we do not have to think about the design only of the material, but we have to learn how to use these membranes, this material. And it is really important to work in the logic of the identification of the operating condition that allow to maximize the performance of our system, in this case of our reactor. So at the end, we identified the operating condition in terms of space velocity, temperature, pressure that allowed us to maximize the performance of this reactor. Comparing with traditional reactors that we can find in literature, we found that also, even when we operated with a higher space velocity, the continuous exposition of catalytic layer to a permeating flow can effectively limit the deactivation of catalytic sites induced by water vapor and depletes secondary reaction. And this membrane was used for more than 4 months in continuous mode without any suspension, and the performance were really stable. So this was a very interesting results on this. The second case study is the use of photocatalysis in membrane reactor. How can we integrate photocatalysis? We know that CO2 can be converted by irradiating it with UV lights. This is a very green operation because you operate at room temperature and ambient pressure. You do not need to supply energy because you use solar energy that could be directly transferred and stored as chemical energy. However, the main issue of this process is, of course, the very, very low conversion of CO2. What we did was to do a step forward with respect to the state of the art. So for the first time, we decided to use membrane reactors in a continuous mode to explore the performance of this reaction. In the most of literature until up to date, all works are carried out in batch with the aim of characterizing the performance of the catalyst. Again, here, the aim was not to investigate the kinetics of the performance of the catalyst, but the performance of the unit. In the logic of scaling from a TRL 2, typical of this reaction, to a higher level of TRL. So what we did was to create a mixed matrix membranes, embedding a photocatalyst in a polymer matrix. Why this? Because as I mentioned before, this allows to give a better exposition of catalyst, not only to reactant, but in this case also to UV light. It allows also to tailor the contact between reactant and catalyst, to reduce the formation of aggregates that usually, or preferential paths that usually occur in a packed bed reactor, and also have an easier recovery of catalyst when it is expired. So the requirement for this reaction was to use transparent polymers like Nathion, Iflon, PDMS, we use Nathion, and the photocatalysts that we used were titanium dioxide, but also carbon nitride and composite catalysts. And here you can see just a picture of the membrane that we did, one of the membrane that we did, and the CEM where you can see the disposition of the catalyst. It's really important to say that also during membrane preparation, opportunely tailoring the the parameters, how we prepare the membrane, it's possible to promote the segregation of the catalyst on one side or other side of the membrane to avoid the formation of aggregates, to enhance the distribution in all the layers, independent of what we want at the end. So at the end, as I mentioned, we use a continuous mode system. And since this reaction has a very low conversion, to be sure that at the end what we had is methanol, ethanol, or other species that are produced by the reaction and not that are coming from the degradation of the material or from the residual of solvents in the membrane preparation, we developed a cleaning procedure. So before starting the measurement, we did a cleaning that is feeding the system with the water and argon instead of CO2, simulating the reaction condition, but in a continuous mode for up to 30 hours. When we did not observe any other product coming out from the reaction, we were sure that the system was ready for operation. So we observed that the production rate of this reaction was strongly dependent on how do we make our material, our membrane, and in particular, independently on the amount of catalyst, the key point was the good dispersion of catalyst in the membrane. So we developed some strategies to enhance this distribution, uniform distribution in the matrix. But afterwards, what we did was also in this case to investigate the operating conditions dependence in order to promote the reaction, but not only. Also, in order to identify what condition can favor the production of one species instead of another. So here, for example, you can see that we analyzed the dependence with the feed-molar ratio. And here you can see that a very low feed-molar ratio, we had a strong production of formaldehyde, but at a higher feed-molar ratio, we had a strong production of alcohols, so of methanol and ethanol. We understood the reason for this. I will not go too much in details, but this is just to show you how much is important not only to work on the material, but also on the process, because it gives you the opportunity to design your operation. Here, just another example with the functionality with contact time, where we understood that operating with a low contact time promotes the formation of alcohols, while operating with a higher contact time, even though in principle can favor the total conversion, however, depletes the formation of alcohols, because the oxygen produced by the reaction can give back reaction, so can again oxidize towards CO2. Of course, a strong dependence there is also on the type of catalyst that we use. So we understood that the presence of titanium dioxide favors the production of methanol, and in particular, while in the case of composites catalyst, we had higher productivity but lower methanol selectivity. So far, the results that we obtained were the highest among those reported in open literature up to date. And this was mainly explained by the fact that using the membrane reactor, we had a better exploitation of the catalyst, a better exposition to the light, and a better exposition to the reactants. So as a final remark, what can I say? It's that we observed that membrane reactor can represent an innovative unit operation for the CO2 valorization, and that membrane engineering plays a fundamental role in the integration of new unit operation in existing plants, and also in the definition of the knowledge necessary to drive the process. So this resulted in the understanding that in the case of the first reaction that I showed you, it's really important to use membrane because the membrane can promote the stability of the reaction thanks to the continuous exposition of the catalytic layer to a gas flow that limits the deactivation of the catalytic sites. While in the case of the photocatalytic membrane reactor, we understood that the use of a continuous process, in particular, doing a step forward with respect to the state of the art, allowed us to deplete secondary reaction and obtain best performance with respect to that achievable up to that. Before concluding, I want just to introduce you a project. ITM is the responsible of the virtual testing and characterization lab of the INOMEM project. INOMEM is a project that goes in this direction, not on the study of the material itself, but on the study, on the development and scale up of nano-enabled membranes and membrane process in various fields like water, energy, and biotechnology. And with this, I want to just share with you introduce you the next Euromembrane conference that will be organized by CNR-ITM and Universita di Bologna in Sorrento in November 2022. And in that occasion, we will have also a dedicated INOMEM workshop. Thank you very much for your attention.
Thank you very much, Adele. Is any questions from the public? I don't see any question. If somebody will put question also later in time, don't worry, send us. We can discuss at the end, or we will answer you if we receive any message.
There is one. There is one. Yeah.
Domanda e risposta is one.
So I can read it, Marina Mikari. Yes. Thank you for the interesting talk. Are there strict requirements on the purity of CO2 fat to the photocatalytic reactor? Yeah, that's an interesting question. So are there any strict requirements on the purity of carbon dioxide?
Yes, there are, in particular related to the presence of contaminants like H2S that often you can have when you treat, in particular, for example, biogas. In that case, it's really important to remove this kind of contaminants. There are no big issues about water vapor, of course, but there are some issues in some cases for some catalysts, not for membrane, related on the presence of oxygen. So when the oxygen is too much, in that case, of course, it's not good to, we have to remove it. Different story in the case of methane, it can be accepted, it's not a problem for the catalyst, but mainly related to contaminants, so H2S, sulfuric compounds.
Can I add a comment to this? There is a lot of interest today, as you know, on, and we are in a hurry to fly to Mars. Do you know how it's done, the atmosphere in Mars? It's 92–93% CO2. So if you look into impurity, check what is the other 7–8%. That will be important. There will be much more interest in the reaction we have been describing. No, CO2 plus hydrogen. In Mars, there is water. And as you know, there is no evidence of oil. But CO2 plus hydrogen can produce methane, methanol, etc. So the real problem is, and people are already doing, we are already looking to this, is what is the impurity in Mars? Forget about the Earth.
Yes. Yeah.
Other question? I cannot read the question here. So
maybe there is another one. How membrane leads to a 100 specificity on demethylated production? Yeah, mainly is related to the contact time that we have between reactants and catalyst, and then the continuous removal of products from reaction volume. So the main advantage in use of membrane is related to the fact that you can modulate the removal of reactants and products, so also to desorb easily and in an easier way with respect to traditional reactors, and this can lead to a higher selectivity of the desired product.
Perfect. Other question? I don't see it. Adele, thank you very much again.
You're welcome.
And ready to discuss more. And now we are moving to the third presentation. The third presentation will be given by Dr. Elena Tocci. Elena Tocci is not a chemical engineer. She's a chemist, but she's the one that started to work introducing molecular dynamics and molecular simulation in membrane system in one of the first European program already in the late as the MELPRO and PERMOD. And the title of her presentation will be just molecular simulation for scaling prediction, the case of nucleation and growth. And as I mentioned, she's just working only on this line where there are a lot of opportunities today in the membrane studies. Please, Elena.
Thank you, Professor Drioli, and welcome all to this presentation. As introduced, I will essentially discuss about the use of modeling tool in the membrane engineering. We know that the third paradigm of this, the process intensification, relates to the integrated multi-scale approach for process innovation. This is quite important. So it requires that we know the at molecular level the properties in order to know the organizing level of complexity within the concept of the chemical supply chain. So also the dream of all people doing simulation is essentially to find a hierarchical approach, starting from quantum mechanical, so from the knowledge of the basic behavior of a molecule inside, going then to the process simulation. It's clear that this is start to be quite important, especially if we are interested in materials, but also in studying not only new materials, because it is possible to optimize some material selection for existing application, but also to contemplate new membrane-based process that could help to be more economical, energy saving, environmental friendly. And this is, we know already that membrane engineering is fast growing, and it has a multidisciplinary character. So the contribution that to the solution of strategic problem of modern society are evident, because we can find solution to problem that world is facing, like water scarcity, energy crisis, raw material depletion, like what happened to the natural elements. And we discovered that essentially with the modern use of all these elements, for sure, in some years, they will disappear, especially when we, and some of them are also really key point from in conflict areas. So we have to face several challenges, and one of these, especially referring to the mineral depletion, is the use of the membrane crystallizer. It is membrane conductors. In this case, we use microporous hydrophobic membranes to create a controlled supersaturated ambient where salt can nucleate and grow. This happens because essentially we start from membrane distillation, so it is a vapor pressure gradient, and in this way volatile compound can evaporate at the interface of the membrane. That to be microporous and hydrophobic, can diffuse or convect through the membrane, and then can condensate on the permeate side, leaving the salt solution to be more and more concentrated, with the formation at this point of nuclei of crystals and they can grow. The applications are several, both in terms of inorganic salts, so from brine, from desalination plants, but also small organic molecules or biological macromolecules. So it's been used both for drug or proteins. And the advantages are different because, first of all, we can control, experimentalists can control the supersaturation degree, the rate of its generation, so the kinetic can be increased, and this could be applied, the method could be applied on a large, small scale for different, also scientific, but also technological and industrial field. As we said before, in the order to know the new operation that require new appropriate membrane material, it is also useful to apply computational tool, because they are playing a really increasing important role. And so the idea was to start studying at molecular level the crystallization of sodium chloride. And we were interested in studying the nucleational growth of salt on different hydrophobic membranes. In reality, we concentrated on PVDF, but in different forms, both amorphous or alpha and beta polymorphs, but also including graphene material in different concentration. And what we observed was really interesting. The materials, so one is PVDF, that is really interesting, is widely used on one of the largely used materials for as membrane conductors, but it's really interesting because it has several phases. Here we describe only 2 of the 5 phases, that is alpha, that is non-polar, and the beta phase, that is polar. And this beta form, that is also most thermodynamically stable, has really interesting properties in sense both of higher mechanical strength, but also due to the polar surface is also interesting for fouling, to reduce fouling phenomena. On the other side, we were also interested in including bidimensional materials in PVDF membrane, because we know that these nanostructures can also improve the performance of the materials. The final goal was to study sodium chloride structures, so to observe into the simulations the phase center cubic structures. All these simulations were done using both the solved systems of the OBIA software, but also GROMACS. Both are molecular dynamic simulation. One that GROMACS is also free and can be directly downloaded. And the models, so starting as any model for use in molecular dynamics, we start directly building atoms as soft sphere. So we first built the polymeric chain and the amorphous structures, or the alpha and beta structures of PVDF. Clearly, these are ideal systems in the sense that we know that experimentally it's quite difficult to find that 100% of beta phases as well alpha phases. You can find these in larger and different amounts, but we were interested essentially to see the direct comparison. So the analysis was to observe the differences in behavior when we have such different phases. The density were that found experimentally, and also we built the PVDF with graphene in different amounts, here 5–10%, and then we approached water solution, so sodium chloride into water, to these polymer structures. The other limitation that we had, but is quite important, is that essentially we were considering dense systems. Now we were speaking about microporous hydrophobic, so microporous structures. This because we already considered that the distillation stage has appeared. So we already used a concentration of sodium chloride that is quite in the limitation of the supersaturation. Essentially, we were interested to see what happens at the initial state of the formation of the crystals. And for this reason, you can see here in the table that all the initial concentration are quite high, real in the limit of supersaturation. It means that just with some nanosecond of simulation, in this case, it's in the order of hundreds of nanoseconds, we can observe then the formation of crystals. Here, in reality, is a comparison of the experimental data that our student was Maria Luisa Perotta performed during her PhD thesis, observing the different formation of crystals when different amount of graphene were into the PVDF membrane. Really nice pictures, but what we obtained at the end was also a nice picture of a crystal. Really, the dimension was quite smaller. So after 200 nanoseconds of simulation, we were able to observe the formation of a center cubic with a size that is the same as that observed from diffraction measurement. Clearly, we started analyzing first how these ions were approaching. So the simplest way is just to see how they see each other. and to count the first coordination number of these. And we can see that the faster crystallization here is when the PVDF is with graphene, both 5% and 10% in comparison to the pristine PVDF. We have also to say that here the final coordination of sodium chloride never reach number 6, that is the perfect cubic crystal, because there are several ions remaining in solution because of this relatively small size of the system, although we're speaking of thousands of atoms. On the other side, analyzing the amorphous and comparing that to the alpha and beta PVDF, we see that we have the opposite behavior. So the amorphous structure is much faster in crystallizing, so in formation of the sides of nuclei in comparison to the alpha and beta. And as before, we never see a perfect crystal. On the other side, we observe that as the sodium chloride approach each other, then the water molecule that were first surrounding the ions are disappearing. So in a way, we can observe also that the coordination of sodium, for example, and water drops from about 5.4, that is also lower than about 6 at infinite dilution solution, because the cation-ion coordination number surges. And this happens clearly the same also with alpha and beta. And in the same way, as alpha and beta are slowly forming the crystal, as also they leave the water interaction also much more slowly. From here, then we are able to observe also the nucleation. What we can see here is the average number of ions of the center of, in case of beta PVDF. We can see that at the beginning, here we have the ions that are in purple and green. They are in a disordered way. And at certain point, they start to organize themselves in more ordered pattern, forming later of more ordered and larger structures. So essentially, we can see we have at the beginning local region with high salt concentration, but then we can find anhydrostable crystal that develop slowly as the system evolves in time. The final result, so, can be seen also here, for example, for amorphous PVDF. We can see that at the beginning of the simulation, we have quite an homogeneous system, but then soon, in some nanoseconds, we can see that the structure are with organized ions. We cannot see the beautiful structure that we can see from experimental point of view. We can see it's kind of inhomogeneous, inorganized salts, but to observe also this formation, then we used another method that was Yasuoka Matsumoto, indicating the change over time of the number of nuclei larger than a certain threshold. So we can observe four domains. The first one is where essentially we cannot find a nuclei larger of a critical size. Domain 2 is when these size start to increase. Domain 3 is where it is stopping the formation, but is kind of reorganization or coalescence of the ions. And then domain 4, that is when these nuclei start to enlarge. Clearly, to observe this, we had to use also a DBSCAN software, that is the density-based spatial clustering of application with noise. That in this case, cluster represents a group of ions that are connected. So the algorithm works considering a certain number of ions that are in a dense region in comparison to others that are in a lower dense region, and the distance of these ions. Considering this algorithm, we were able to observe so the critical nucleus of ions the atoms. Then we were able to calculate the computational induction time, and from the slope of the domain 2, we were divided by the volume of the system. We were also able to calculate the nucleation rate. What we can see here, we observed that the amorphous has larger nucleation rate, and in parallel, this because also the computational induction time is much lower in comparison to alpha and beta. They are almost in the same range. And this means that also the dimension of each nucleus is also different. The critical nucleus for the amorphous one is about 13, 14. It means that under this value, no stable nuclei are found. So it's a kind of formation and dissolving of the ions. But for alpha and beta, the system could be also larger, going in the range of 19. The comparison with experimental available data. First of all, we have to say that experimental induction time can be observed from pictures. So from SEM micrograph of crystal pictures. So the dimension of this number is in minutes. And the available data clearly are also for bulk solution. We did also this simulation for amorphous, and then for PVDF structure containing graphene in different amounts. Beta and alpha clearly are hypothetical, so we have only the computational data, but it's essentially what we want because we would like to give prediction. It's clear that we speak about nanoseconds and the experimental one is minutes, but we can say that the trend is quite good for us. And we can observe that essentially we have a good indication. So we trust also that alpha and beta will have different experimental nucleation time, maybe modified because the amount of alpha and beta will be less, but the trend will be this. Why we have this different behavior, which is the reason why including having just alpha and beta could behave in a different way than just the amorphous structure. We decided to observe the amount of water, so the water uptake at each time, at the nucleation time, and then also for some where we were just counting this at 10 nanoseconds, 20 nanoseconds, 200 nanoseconds. The real important thing is that for alpha and beta, the numbers are lower than in comparison to the amorphous and alpha, and then with graphene at 10 and 5 and 10%. Clearly, these numbers are relatively near, especially for alpha and beta, and but the difference and are also small, the difference, but we know that this changed completely the formation of the nuclei. And the reason is essentially explained also on the capability of the material to keep few molecules of water from dissolution, so increasing much more the supersaturation. Alpha and beta are a packet system, so the chain cannot have so much free volume. So water molecules, especially because PVDF is hydrophobic, so tends to not to like water, have difficulty to go in through the chains. The amorphous structure has a certain amount of free volume, and we checked also that the amount of free volume with the nanostructure, so graphene in different amount, was also much increased. And here, this is just an example, because we found that this structure of graphene is anyway located at the distance that is about 3 angstrom from the PVDF chain. So water molecules can go through this space. And this means that there is the possibility of water to move. Here in the slide, we speak about interaction. It's clear that there is no interaction between graphene, that is hydrophobic, also and water. But this function means essentially that due to the free space between the polymeric chain and the graphene oxide, water can also go better in this area and prefer to stay in this area. So this peaks means essentially a specific kind of how the oxygen of the water sees PVDF, that is quite no difference in comparison to what sees graphene, or better, the free area that is between graphene and the polymeric chain. And this explains essentially the behavior, the different behavior of materials. So the different structure of and the different morphology of PVDF completely change the crystallization of sodium chloride. On the other side, we can also see how the distribution of small nuclei were available for amorphous alpha and beta. So here we check the number of nuclei both in time and in size. And we can see that for the amorphous structure, this is smaller because the number of smaller here is quite higher in comparison to the other, but is quite more regular cluster. Alpha and beta in reality have the smaller area is missing in comparison to beta, so alpha produced more inhomogeneous and structures of crystals and also of small dimension in comparison to beta. Now, let's go to the conclusion. So essentially, we saw, which is how much powerful is the use of computational tool, and not only to observe the what happened into the PVDF structure, so to explain the behavior of water inside the PVDF structure. So we were able to see the influence of different PVDF systems, and we can see that essentially we have different behavior if we speak of polymorphs, if we speak of amorphous system, or if we include graphene in different amount into the structures. And we can see that in all the systems, the nucleation time is going to be enlarged. This depends on the water uptake. So it's a combination of the morphology of the material, but also of the behavior of the water. And this means that also that the size and the homogeneity of the crystals also change, going from much more inhomogeneous and small dimension alpha and beta in comparison to the amorphous one, and larger than amorphous if the nucleation time starts to be larger and larger. And this is essentially an indication that if we want to study new material, or if we want to predict also the formation of other crystals, also considering other structure, we have to take into account also the morphology of the material. So clearly what is needed is also to predict using also the intelligence, artificial intelligence. This means that we have to work a lot to produce a lot of theoretical data, but for sure this will be our dream also to reduce the experimental activity. So with this, I think that I would like to acknowledge all the people working, giving several suggestions, both students and also colleagues, the project funding, you for your attention, and as all my other colleagues, also I would like to invite you to the your membrane. Please consider the registration and abstract submission is now open. Okay, thank you.
Thank you, Elena. There are questions. I see some questions. Elena, you have 2 or 3 questions.
Okay.
Can you read them? Yeah.
Okay, questions, let me see. I totally agree that is very adapted for a better understanding of molecular interaction from which macroscopic parameter can be strongly dependent. But how to fill the gap between such model and the one used to describe fluxes, for instance? Okay. The gap can be filled using several other approaches. the molecular modeling, so we can have information at molecular level, and we can give information and give suggestions going to the next stage. That could be mesoscale stimulation, and from mesoscale, then we can go beyond. So the point is always to find linkages between different stage and level of simulation. And so I think that the next point will be to link all this information. It's clear that anyway, the important thing is that the important point is that we have to think also of the influence of molecular level structures, also when we describe fluxes, and also when we describe the system as complete.
Another question?
No. Okay.
No other questions? Elena, thank you very much again.
Thank you.
Remind that I think it's molecular modeling can give a lot of contribution to anticipate or to predict transport phenomena in membranes in all the different operations that we are going to cover. And until now, it's been used, but not enough, in my personal opinion. So that was there's much more that can be done, and we need more fresh people, more young people active in this area.
Yes.
Thank you very much again. Next presentation now is no more the ITM, is coming from the Chemical Engineering Department of the University of Roma La Sapienza, Roma 1, and it will be given by Professor Marco Stoller. Marco Stoller is just working at the Chemical Engineering Department, and he's will discuss on development of advanced control system and proper tools for membrane processes. Please, Marco.
Yes, thank you for your kind introduction. Indeed, I'm going to present something which is very important also for process intensification purposes and targets. That is process control, and in particular process control on membrane processes. Indeed, it might be, I'm trying to find the presentation to share. Okay. No, this is not the correct one. But somehow strange because I have not the window. Wait, I have to. Okay, I'm going to load the presentation again. And nevertheless, let's say that control of membrane processes is something that is much more near when we may initially think, because indeed life, as we know, is not only but mostly membrane based. Our body is a agglomerate of membrane processes, and I must say that also working in very harsh conditions sometimes, no? Therefore, we have solid liquid phases, we have all kinds of membrane processes. And one thing which is very important for us is that our membranes has to work constantly with constant performances during our life. I must say that nature in this sense has make a very good work in making our membranes long lasting for 100 or more years, and in maintaining these okay, finally I have found the presentation. So maintaining these performances constant. This is something we want to do also technically in making our membrane processes, and we will see that it appears to be an easy task, but it is not that easy. So making a quick introduction to control systems. First of all, what is a system? A system is a collection of components which are coordinated together to perform a function. Normally, our system will be our membrane process, which is a unit, a so-called unit in process engineering. We have to separate system from a dynamic one, which is a system with a memory, meaning that the system is affected by what happened before. And this will be very important for our membrane processes, since our membranes will have memory of what happened to them before during operation. A system interacts with the environment through a controlled boundary. And this is where we can act on the system in order to perform our corrections and in order to lead the system to operate as we wish. There are two aspects which should be noted from the beginning at this point. We will build up a system which tries to control a system, meaning the control system is indeed a standalone system by its own and is affected by the same problems as the system he tries to control. And concerning membrane processes, fouling, if fouling is accounted, if fouling is a major issue to the process, our membrane system will upgrade to be a dynamic one, meaning that fouling will affect the history of the performances of a membrane and will affect in the present and in the future the membrane. Indeed, if in other words, fouling will change the membrane to be another membrane. The membrane is not the same as before, meaning that indeed we will handle and we will try to control a membrane which is not the same as we have brought from the supplier as a new one. So what we are going to do is to make things more easier than normally accounted in let's say by building up fundamental equations. We will try to express our system by a black box approach. We are not interested what is indeed the system. We want only to know how the system reacts to given inputs, which might be disturbances, might be inputs from the environment, but might also be, and this is where we can act, input given from our control system, which enters the system and will give as a result an output by means of a very simple transfer function, so-called transfer function, which ties the input to the output together. Control is the idea to deliver to the system an input such to lead the controlled system to maintain a desired output value, which is the set point. This is this is performed in order to guarantee constant performances of a system in the long term of operation, but also for other objectives, which may be the safety of the process. We don't want the rupture of our membrane process, which will be a big loss of the investment costs we have performed to build up the membrane plant. The safety of a personnel, which is nearby the plant working. And it is also connected to the possibilities for economic optimization, for example, reacting to particular market needs or to market need changes. The control can be performed manual and automatic. We are interested in automatic control. Therefore, the control system is an interconnection of different components which forms a system by itself, which has an input signal, which is the set point, the desired value we want to maintain, and will deliver an output to the system to control in order to lead the system to our set point. In order to do this, we need two main ingredients. We need control logics. We need some equation for the control system to work and to tie the input with the output. And we need an energy source in order to let the control system work. And at the end, we connect the control system to the process by means of an actuator, which is normally a regulation valve, by means of a feedback control loop. The process is monitored on its output, for example, flow rates. The flow rate is measured by a sensor. The measured flow rate is then compared to the desired flow rate. The gap between the set point and the measurement is defining an error, a deviation of the system from the desired value. The controller will feel this error and will try to act on the valve in order to nullify, in order to make it zero, this error in time. The process is affected, of course, by the action of the controller, but also by the disturbances. For example, differences in pressure, which means differences in or deviations of the flow rate. The feedback is the basic control scheme used in process engineering, and almost all, near to 100% of all control systems are feedback-based systems. The advantages of a feedback system is that it will always trigger an action as soon as an error is measured. So whatever is the disturbance, and we don't know the exact nature of a disturbance, the error will cause an action of a control system, which will try to compensate this gap as a function of time. But there is a big disadvantage of this approach. That is, the feedback, in order to work, needs an error to trigger, meaning that in some cases, the deviation has already occurred, meaning that we have always the deviation, the disaster going on before being able to perform an action. It is not possible by feedback control systems to foresee somehow to predict in future the behavior of a system. We will only react on present situations, trying to make it better in the future. Control logics of a feedback controller are mainly three. Here, very shortly mentioned: proportional integral derivative. You see that in case of uncontrolled process, in case the controlled variable, for example, flow rate or temperature, increases, it will increase up to a plateau value, which is given by the physics of a system. In case we have only a proportional control system, it will mitigate it will perform an action and will mitigate the occurrence of a deviation from our desired value, which is here the x-axis, but with some offset. This is due to the fact that, as we have mentioned before, feedback controllers react with delay to what is causing the deviation, meaning that the proportional alone is not able to gain back the deviation as a function of time. It will perform its action and will keep its action active, mitigating only the deviation. In order to nullify the error again, in order to nullify the offset, we need the integral part, which is a logic which integrates in time the past errors and tries to compensate these past errors with a enhanced action of a proportional part, and we can stabilize normally the derivative, the PI response by putting also a derivative action to our controller. I'm not going inside the equations, of course. This is not meant to be a process control lesson, but indeed, it is important to know that feedback controllers relies on these three main logics only. In membrane processes, the main interest is to control performances in terms of permanent fluxes as a matter of time. Now, going to membrane processes, we have mainly two possible control strategies we might apply by using only feedback controllers. The first one is the constant permeate flow rate, which is normally the one preferred by industry, since this guarantees that the capacity of a membrane plant is always constant, delivering always the same amount of permeate during operation. In order to perform this control, you put a control system on the flow rate of a permeate, and you manipulate the pressure on the concentrate side. If the flow rate is going to drop on the permeate side, you close the valve on the concentrate side in order to gain pressure, and then increase the pressure and increase the TMP value, automatically increases your fluxes again, your permeate fluxes again, and so the flow rate of permeate is going to increase again and to reach again the set point value, the desired value, which you want to keep constant. In this strategy, in the best case, the blue line, we have the flow rate of the permeate, which is constant in time. We are going to the black line afterwards, which is going to interfere with this basic idea. But ideally, it works perfectly. The second control strategy is to maintain the operating pressure value constant, the TMP value constant. In this case, what we are going to do is to measure the pressure value on the concentrate, and we are going to close or to open the valve after the membrane module in order to maintain this pressure constant. We are not interested in this case how much permeate flux we will obtain. So it might be that the permeate flux suffers some variation in time. But here the important thing is to maintain the pressure constant. In this control strategy, again, if the pressure drops, you need to close this valve in order to gain pressure over the system, and as an side effect, we will have the permeate stream which will increase. In this case, if you are maintaining your pressure constant, the fluxes, the permeate flux we will normally observe is a decreasing one, such as shown here in this blue plot, mainly given due to phenomena which occurs during operation, which might be differences in feedstock concentration, therefore differences in osmotic pressure, or even membrane fouling, of course. Again, we are going to the black line afterwards, as soon as we introduce JB, the boundary flux. So all control systems involves the measurement and control of permeate flux rates. The control system is successful as long as the permeate flux do not overcome JB as seen in the plots before. This condition is met only if fouling is membrane fouling is limited phenomena of a system. In this case, the system is not dynamic, is a static one, and the control logic holds constantly as a function of time. Once we set the control logic, it works perfectly because the system do not change as a function of time in its properties. Other control systems, normally involving membrane technologies, may include the control of a feed temperature, differences of pressure crossing the membrane module, which is important, for example, for spiral wounded module, where we need to constrain, to limit the difference of pressure at the inlet and the outlet of a module in order to avoid membrane rupture, module rupture. In situ real-time analyzers on all streams, for example, concentrations, or offline analysis on feedstock for some chemical analysis or chemical composition analysis. The big issue is if fouling becomes important to the system. In this case, we have already seen that the system becomes dynamic, because the membrane will not be the same as before, since fouling will unavoidably change the membrane properties. In this case, a control system which was set to a new membrane has the difficulty to handle the present membrane partially fouled by means of the same logics. It is it's like to put a control system on a sport car, and when this sport car in time becomes a smaller car, powerless car, and we try to control the engine with the same logics as adopted on the sport car. It's going to be very difficult to perform this kind of action. So as soon as the system reaches severe fouling conditions, the control logic will start to fail. And what is going to happen at the end, for example, in our strategy of maintaining the permeate flux constant, is that if the fouling, the black line, you see is crossing the blue one, at this point the fouling becomes predominant and don't allow the membrane to guarantee the performances we want, we had set as a set point before, meaning that at the end the membrane will collapse in performances and will follow the collapse of a system, which is indeed the collapse of a membrane under fouling. And what is happening to the membrane is that the fouling will occur on the membrane module. This is an autopsy on a spiral wounded membrane module. You see it's completely coated by organic matter in this case. And of course, it's not a novel membrane. So the performances in terms of fluxes of this membrane are surely less than those observed when the membrane was new. The control system has to adapt to this new membrane, which is not fouled, but it's less performance membrane. So indeed, the main challenge in treating, for example, olive mill wastewaters by means of membrane processes, pressure-driven membrane processes, is to strongly inhibit membrane fouling. Of course, we need the high productivity and the high longevity of the membranes. And solutions to this is to inhibit fouling phenomena, to increase the boundary flux values of a system, if possible. But another strategy is to develop advanced control systems which are capable to take into account the fouling as a function of time. Briefly explained about boundary fluxes. If you operate below the boundary flux, which means that you have only reversible fouling, what you encounter normally as flux performances of the membranes is the green line, more or less constant with a linear decrease in time during operation. The problem is if you operate the red one, the red dot, if you operate above the boundary flux, then fouling triggers, the permeate flux will decrease as a function of time. This will lead your permeate fluxes very quickly, as you can see, to zero flux conditions, because fouling changes the membrane properties. It occludes the pores, the membrane pores, by different fouling mechanisms, and therefore the correspondent boundary flux value of a membrane will reduce, will change according to the new condition of a fouled membrane. The difference is very important, because the green line delivers reversible fouling, which is recovered by membrane washing, very easy to get rid of, whereas following the red line operation leads to irreversible fouling, which cannot be recovered in no way, even by means of chemical cleaning or harsh cleaning procedures. The boundary flux indeed is a function of a key parameter, if you want to. It might be the concentration of your pollutant. It might be a combination of different parameters of a feedstock. Whereas the range of validity of this equation written below is given between Kp being 0, no pollutant. This means poor water permeability indeed, and a condition where the membrane is unable to handle the concentration. Imagine membrane crystallization. Now, if we go over the saturation value on the membrane surface, the problem membrane crystallization is that we have immediately the formation of crystals on the membrane surface, meaning that we have irreversible fouling of a membrane. In this case, it is not possible for the membrane to handle this kind of concentration. And so in this case, we will have zero flux the conditions meeting at a specific value of a key parameter. The problem is that fouling will decrease this, will shift this plot as a function of time into negative values, meaning that at the end, at T star, unavoidably, even with poor water, the membrane will not deliver fluxes anymore. This is if a membrane is completely fouled, meaning that the membrane is becoming completely impermeable to whatever liquid want to cross the membrane. Okay. This means that whatever membrane we are going to build, whatever membrane we are going to find, to invent in the future, there is no possibility for us to have the Highlander membrane. Okay, the membrane which will long last thousands or 10,000s of years. The membranes have, unfortunately, also for us, limits. We know this very well. We have to keep our membranes of our body health, but we know that we have not Highlander membranes by our own, meaning that indeed we have the same constraint that at some moment one of our membranes fails and life is not sustainable anymore. It is important that this decrease is slow. This is exactly what we do with our membranes ourselves. We are trying to keep healthy, meaning that we want to decrease the unavoidable decrease of our membrane performances, but we want that this decrease is as slow as possible. So the problem is that even operating below boundary flux values, there will be a loss of performances during the operation, meaning that even with no fouling, due to aging, the membrane is still weak, but it is still a dynamic system. Therefore, advanced control systems are, even in that case, desirable. In order to design advanced control system, we need tools. So we are in our research lab, we are trying to build up, for example, for Aspenhysis, a membrane custom unit in order to enter data concerning also fouling issues and capable to be used as a Aspen HYSYS unit, membrane unit. Aspen HYSYS lacks on membrane units on its standard library. So we are trying to develop this membrane unit, which is compared to other existing and available on the internet. It includes also fouling behavior. So it's a dynamic unit entirely programmed in Visual Basic within Aspen. And it is possible also to implement these models within LabVIEW, for example, within software which is able to perform process control. In our case, we are trying to develop a predictive adaptive control system. The predictive part is given by a model and tries to simulate all possible conditions encountered in the past, so taking historical data from the membrane plant, and to it tries to track back what happens to the membrane system in order to see if there are deviations from expected behaviors, and attributing to this difference of behavior a specific amount of fouling ongoing to the system. This data, this information is then used in order to predict the behavior of a membrane system in the future, meaning that the hypothesis is that we know how much fouling is forming. We take this formation of fouling as a constant. We will apply this constant fouling formation in the future of this membrane plant. But then, after some time has passed, we check again what happened before, and so we check if our prediction was correct. If our prediction was correct, we are describing very well our system. And so we can continue to use this fixed amount of fouling which is forming. But if our prediction was not correct, if our prediction is different than the historical data of a membrane plant, we have to adapt the control system. We have to change the parameters of a control system in order to adapt to the new membrane, which is more affected by fouling than expected. And this is done by the adaptive part of the model, which tries to tune the control system in order to have a better prediction in the future and to be able to follow the system better in future. So indeed, we are putting the set point algorithm inside our feedback control. So our set point is not a fixed value, but it becomes a variable in the system defined by the control system in order to meet set points which are possible to achieve in time. So it's not a fixed set point which might not be possible to guarantee, but we can lower the set points values to an algorithm capable to calculate set points. And so it is possible, you see, to dynamically the system will on permeate fluxes, recoveries, TMP values will define time by time different set points in order to lead the process during its progress of fouling, triggering and affecting the system during the whole operation, to lead the system more constantly in performances. And the control system is also capable to catch disturbances very quickly. This as a HYSYS simulation only, so it's not a real system. This is given by the custom unit we have developed. So it's up to now only a simulation, but it is able to catch with very interesting values the error, the deviations, and to lead the system back again to desired set point values. Again here, the figure is a little bit not very defined, but it had to be zoomed, because else we cannot feel the small deviation the control system allowed the system for deviation of 20%. So in this case, we have forced an error of 20% of an error in our estimation, in our prediction, and the adoption of this 20% follows immediately, a straight line follows immediately good control of the process. What we are trying to do nowadays is to transpose what we have done as a simulation in Aspen to, of course, a lab scale membrane plant. So we are implementing a very small membrane plant, but it has a spiral wound modules. So it is exactly the same modules which are commercially aviable. It has, you see, electric valves, and you don't see the computer system. It's here, but here you see a screenshot of a computer system. You can handle all the control systems separately. And what we are trying to do is to see how our control systems are working according to the theory we have developed in Aspen analysis by simulation. Here we have examples of tuning of a PD controller. So we have up to now implemented only the feedback control system, and trying with a feedback control system to control the TMP. You see that a deviation of TMP going from 0 to 7, the desired value was 7. The system immediately reacts in order to maintain this control constant. Up to now, it's not much different than all those control systems, which are 99% mostly used in all membrane plants. So we arrived at a point where we have this small membrane plant, reliable, on which we can finally this year implement our advanced control system. So going to the conclusions, and I'm sorry I'm 2 minutes late. PD controllers can be successfully used for membrane processes that do not exhibit severe fouling issues. If fouling triggers, PD controllers may fail. And therefore, advanced control systems, tools, the development and the implementation of these control systems may overcome the practice to use only PD controllers, which are very limited in application, and do not avoid process failures. Develop tools, for example, those in Aspen analysis, needs to be developed in order to design optimized membrane processes capable to account fouling problems. The implementation and validation of membrane plant will be performed in the next future, and further investigations of specific control logic algorithm beyond the adaptive predictive one I've presented here are on the way. So thank you very much for your attention. Sorry, 3 minutes more time than expected. Ready for questions. Thank you very much.
Thank you, Marco. Thank you very much. So we are at the end of our session. There are questions. I think you have 2 questions if you like to answer.
I'm going to read them. Okay, very nice application of adaptive control strategies. Would all this be effective also with other non-ideal phenomena, membrane or scaling? Yes. The control system is based on black box approach, meaning that indeed the fouling description is not something that uses equations. The boundary flux approach is not something that describes the fouling mechanism. It describes only that you have performance loss due to some phenomena, which is not specified. This is the limit of the theory, but it is the great value from an engineering point of the theory, because it allows to answer yes to this first question, meaning that also other phenomena can be taken into account by means of boundary flux theories. Second question. Controlling a raw operating pressure by closing a valve may not be the most energy effective strategy. I agree. would you suggest current or future alternatives more effective than this one, and how would you implement if in the presence of pressure exchangers? I'm focusing only in this presentation on the control of membrane processes. Of course, the control system is normally organized as a DCS, as a distributed control systems. It is the control systems normally covers also the interaction between different units that might be the membrane unit and the pressure exchange unit. So in this case, you have to extend your basic feedback controllers if you want, and you have to deliver some supervisor, control supervisors of all these controllers on your plant. Answering the question probably will take a very long time. It is possible to use advanced control systems on single units and to merge these advanced control systems together in one supercontroller. By the way, the supercontroller is also able, again, not only to technically optimize the process, but also to economic optimize the process. Meaning that, for example, it can take from the internet the price of energy and can accept some operating conditions if the price is low, instead of high energy prices, which requires to throttle down the operation. So indeed, control engineering is more complex than only controlling process control. But again, it is very important that, in my opinion, that we start to think about advanced control system on membranes, because one of the problems of membrane technologies in the past were membrane process failures or over design or unexpected loss of performances. All this can be now avoided by proper design, new materials, better understanding of the membrane separation and phenomena, but also by advanced control systems which are capable to maintain constant our desired operation, our expected operation, taking into account also phenomena which feedback controllers cannot take into account by its own. Thank you.
Thank you very much. No more question. There is any other question from the participants in general? Any comments on the session? If not, Petr, do you like to make some, you are still here, final comment?
Well, I have spent a very nice morning. It was very inspiring, and all lectures I found extremely interesting. So thanks, many thanks from the side of EFCE board. It was a great morning, and maybe Martin may add something. Thanks to you, Enrico, to all speakers, and of course to all who attended this workshop. I'm very, 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 very excited about it. It was a very nice morning for me. Thanks a lot to all of you.
Thank you very much. Well, if I can, I am also pleased about this morning. It'll be interesting to go through the different presentation. I'd like just to mention that, as we have been discussing some other occasion, from my point of view, can be interesting to continue this kind of events. And I'm following from a number of participants. We had many more participants than when you attend a session in a traditional conference, by the way, let me mention, in some large place, etc. So that can be effective, and can be still more effective if there will be more also interaction with the potential participants. Adele has been mentioning that the ITM, we are part of a large European program, just focalized of the engineering aspects of the pilot units that we have to put in operation all around the world, particularly starting from Europe, for competing with other countries where these things are done much more in a wider, as China, for example, where they have huge technological park totally devoted to membrane engineering. I don't know if you are aware, I was mentioning China before, let me mention again, they have industrial membrane park of the order of 240,000 square meters, only installation at industrial level, not related to, only related, the academy is 20 kilometers far. This is only for real industrial application. And now they're becoming specific. They are in the Shandong province, and they are in the Gansu, they are in Jiangsu province, etc., all spread around. And the results are on the market now. So we have to try to insist with this kind of action and try to do something similar. And that can be quite useful because most part, by the way, of the action in China are related to the research in Europe. If you go and read this report, you will see that the membrane they are using are the one developed by Evonik, or the plant they are using in reactors are the one that are being developed in France, and so on. But we don't have the same impact. We are not able to overcome the Death Valley. We still are at the bottom of the Death Valley. Going out, this cannot be the only way, but the operation that the European Federation has been promoting at the moment, in my personal opinion, can be effective. So there will be hopefully other opportunity for meeting, and if the interaction with the participants will increase, we can also organize, ITM can take the responsibility also to just have a more specific. For example, Adele, no, we are in charge of the dissemination of Inomen. Inomen is all chemical engineering, basically. All the aspects of in the logic of process intensification, I like to add, but everything is processing, chemical engineering. And the European Union is sponsoring this with a significant amount of money because they realize that people don't know what you're talking about. A lot of people don't know what is changing today, and that we can contribute to just make this project more effective through dissemination. This action of the European Federation is a good example of dissemination. So Adele is in charge of this, we are in charge of this, and so we can contribute with the Federation if there will be opportunities. So thank you again to the Federation, thank you again to Martin and Petr for the organization of this event, and if necessary, we'll be ready and pleased to contribute again. Thank you.
Thank you very much.
Bye-bye to everybody. Thank you. By the way, I apologize. Thank you to all the participants, speakers from ITM and from Rome University. Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.